Good morning, guys. Welcome to day one of our new unit, trigonometry. Today we're going to be looking at special angles. Before we get into any of the special angles, there's a few definitions that we need to know. It'll just take a minute and then we'll get into the stuff for today's lesson. Okay, definitions and things you need to definitely be introduced to. This right here is called your unit circle, and it's a big concept in trigonometry. You just kind of touch the surface of it this year, but you're going to really get into it in grade 12, and it is the foundation for a lot of what we do. So I want you to imagine your Cartesian plane, your x and y axis, and you draw a circle on your x and y axis where the radius is 1. Okay, so the distance from the center to any point on this circle is 1. Okay, it's 1 unit, whatever the units might be. And we've highlighted the 4 main points of this circle as it goes around. Now, in order to get into the trigonometry, we have to imagine that we draw some kind of arm on our unit circle. So this would be like the hand of a clock. If this arm sits on our x-axis, we would call that our initial arm. Okay. And if this initial arm starts to rotate in a clockwise direction and we end up stopping about here, this would be our terminal arm. So our initial arm is the beginning arm. It's where we first start. It starts to raise up a bit. Now we call it our terminal arm. And the angle that you make between your terminal arm and your initial arm, we call this your principal angle. Okay, I'm going to call this one theta. Okay, so this angle theta is our principal angle. Now, a lot of times, if we're talking about a standard position, this is what we're referring to. So if we're talking about an angle in standard position, we would be talking about this particular principal angle. Now, the principal angle, however, if this terminal arm continues to rotate, it might end up over here. The principal angle would be all the way over to the other side, okay? So your principal angle can be all the way over. But our standard position, we would consider it from our positive x-axis. So you'd have to imagine that this kind of gets flipped over and rotated as a reflection, just so you can compare it afterwards. I'm more concerned with your principal angle. Now, this angle that's left over from always your x-axis is called your reference angle, or it's got another name, your related angle, okay? So we're looking at a principal angle, a related angle, this is your initial arm, and your terminal arm. And if we're talking about an angle in standard position, we're always talking about the angle in relation to the positive side of the x-axis, okay, where our angle is at the origin. Okay, I'm more concerned with reference, principal, terminal, and initial. Okay, all right, let's get into today's stuff. So we're going to be looking at some special angles. Oh, I forgot to cover them. So here's our unit circle. I want you to consider your terminal arm has a unit of 1, and it touches your unit circle at any point, and we're going to call the coordinates of that point x and y. Please take a second, refresh yourself on your SOHCAHTOA, right? Your primary trig ratios. Sine is opposite over hypotenuse, cos is adjacent over hypotenuse, tan is opposite over adjacent. So if I come over here and I'm looking at this point xy, the distance from this point down, this is the y value. And the distance from our center or our origin to this vertical line that you drop downwards, this is the x value or the x coordinate, right? So in this case, it's approximately 1, 2, 3, 4, 5, I don't know, 5.3. And coming downwards, our y value is 1, 2, maybe 2.8, 2.9, okay? So we have our angle. This side of our triangle is y, this side of our triangle is x, and we get it because the hypotenuse would be 1. Okay, so take that idea of that triangle and now think about your trig ratios. Sine is going to be opposite over hypotenuse. Sine of theta is y over 1, y over 1. We never write the 1 on the bottom of a number, so sine theta is equal to y. So this y value is really the same as sine of theta. And then the same idea goes for our cos values, right? Cos is adjacent over 1, so cos of theta equals x over 1, because our adjacent side to this angle is x. We never write the 1 on the bottom of a fraction, so x is equal to cos theta. This is kind of the second rule that we're going to look at today. And then the third one would be our tan. Tan is opposite over adjacent. Tan is y over x. Tan is y over x. Okay, so I've highlighted them here. They are written down here for you if you need them. And now the last key to our puzzle, we have these two special triangles. You have to memorize these. If you're making a set of study notes for yourself, this is something that should be one of the primary things on your study notes. These are two triangles that you would get from a square of length 1 and from an equilateral triangle with side length 2. If you go to page 283 in your textbook, they do a lovely explanation of where these numbers come from, because you're probably looking at them going, oh my God, miss, where do they come from? Go to your textbook, okay? Oops. Okay, so in your textbook, they draw a square with side length 1. They draw an equilateral triangle with side length 2. If you cut your square in half, this would be side 1, this would be side 1. Use Pythagorean's theorem to get the hypotenuse. It would be root 2. This one over here, if I drop a vertical line straight down, a perpendicular down, this would be side length 2. Because the bottom is also a side length 2, when you cut it in half, this would be a 1. And then you can use, again, Pythagorean's theorem to get the height. It would be root 3, okay? Right, and because you cut the equilateral triangle straight down, not only does it cut the side length, it also cuts the angle. So that's where these two triangles come from, okay? They do some awesome stuff in your textbook there if you want to continue looking at those pages, but essentially these are the values that we're going to look at. Okay, I just want to pause here to make sure I've got an example for you. Okay, let's take a look at a quick example. So we have those two crazy triangles, and it says calculate sine 45 cos 45 plus sine 30 sine 60, but we want your answers as exact values. So you are not allowed to turn these into decimals. Okay, so this is where we're going to use our special triangles. So let's go to our special triangle, which is down here. And the first one was sine of 45. Okay, so here's 45. Sine of 45, remember, is opposite over hypotenuse. So it's 1 over root 2. Okay, so this part right here, let me get my pen going. Okay, so sine of 45 is 1 over the square root of 2. Cos of 45, let's go back. Let's look at our special triangles. Cos of 45 is adjacent over hypotenuse. It's also 1 over root 2. Okay, so this is going to be times 1 over root 2. Plus sign, now I need sine 30 and sine 60. So we're going to keep these values in our head. Sine 30, okay, here's the 30 degree, boom, okay. Opposite over hypotenuse. Okay, so sine of 30 is going to be 1 over 2. And then sine 60, okay, again, now I'm looking at this angle, opposite over hypotenuse, root 3 over 2. So let's come back over here. Sine 30 was 1 over 2. And sine 60 was root 3 over 2. Okay, now just simplify using your regular algebra rules. 1 over root 2 times 1 over root 2 would be 1 over root 4, because we know how to multiply radicals. Square root of 4 is 2, so this is 1 over 2. And then this one over here would be square root of 3 over, well, 2 times 2 is 4, so root 3 over 4. We are adding fractions. In order to add fractions, you must have a common denominator. So this is going to be 2 over 4 plus root 3 over 4. Now that they have the same denominator, you would add your numerators. And because one is a regular number and one is a radical, you would leave it as 2 plus root 3 over 4. And there is your answer, okay? So you're using those two special triangles to make sure that your answers stay exact, okay? Let's look at one more in a word problem. Oops. There we go. All right, so these are basically the same trig questions you would have seen in grade 10, but we're keeping our answers very specific, okay? And that's the whole point of today. So a ladder is 2.5 meters long. It's placed against a vertical wall, so the top of the ladder makes an angle of 30 degrees. We'll draw ourselves a diagram. Oh, look, a diagram. All right, and we want to determine how far up the wall this ladder reaches. So we're basically trying to find this distance, okay? Excuse me. So they want to represent H, it's fine. Oops, H. So given this angle right here, right, we can use our trig ratios, adjacent over hypotenuse. If you think about SOHCAHTOA, cos uses A and H, A for adjacent, H for hypotenuse. So there's our adjacent, there's our hypotenuse, we're going to use cos. So cos of 30, we're going to write our ratio down, is the adjacent, H, over the hypotenuse, 2.5. So here we go. But I know that cos of 30, based on my special triangles, okay, I'll show it back to you here. Come on, special triangle, there we go. Okay, cos of 30, I'm going to go to my 30 degree, adjacent over hypotenuse, √3/2. So I'm going to replace cos of 30 with √3/2. Okay, isolate for H, bring the 2.5 onto the other side. You solve for H. Now, we want exact values. We do not want decimals. This one happens to have a decimal, so you need to find a way to turn that into a non-decimal. Look at the fraction portion. 2.5/2, that's the same as 5/4, right? Find an equivalent fraction. So we're going to replace this part with 5/4, and you should end up with 5√3/4. And that is the most accurate, exact answer you will get for this particular trig question, okay? Most of the questions you've been assigned are very straightforward. They're more like the first example, but I still wanted you to see one like this. Okay, play around with them. I've assigned you some. If you don't like my questions, by all means, please use the questions in your textbook. Do as many or as little as you feel that you need in order to understand the concepts. Don't go into the crazy hard questions. I don't need you to see those right now. Okay, guys, have a great night. We'll see you for the next section.